In section 2.7, we will be solving polynomial inequalities and solving rational inequalities. Now let's look at a couple of examples. So in this example, we want to solve the given polynomial inequality. All right, we're going to solve and graph the solution set. The inequality is x squared minus x is greater than 20. All right, so the first thing we want to do is to express the inequality f of x as greater than or equal to 0. All right? So let's do that. So this is going to be x squared minus x minus 20 is greater than 0. So that's the first thing we want to do. Number 2, we now want to solve f of x is equal to 0. In other words, we want to find the intercept. So what do? We have x squared minus x minus 20 is greater than 0. So it does factor. This polynomial does factor. All right, and I want to solve first I want to know when this is equal to 0. All right, if I find out where it is equal to 0, we are then finding what is called the boundary points. All right, and we'll show you what the boundary points will allow us to do. So if we now solve the equation, so we're solving x squared minus x minus 20, all right? All right, so what do we have? So if I factor this, I get what? I get x plus 4 times x minus 5. So we have x plus 4 times x minus 5 is equal to 0. Using the zero product principle, we have x plus 4 is equal to 0. And x minus 5 is equal to 0. So here we have x is equal to negative 4 and x is equal to 5. All right, so a negative 4 and 5 are the boundary points. All right. All right, and the boundary points tell us where we allow us to subdivide or divide the number line into intervals. So in this particular case, let's locate the boundary points. So for us, I have the boundary points are a negative 4 and 5. So those are the boundary points. All right, so the boundary points divide the real number line into intervals. Now let's just record the intervals that we have here. All right, so I have the intervals. Let me record the intervals. All right, I'll just keep track. All right, interval. So the first interval is going to be from all numbers less than a negative 4. So we have minus infinity to a negative 4. And we have from a negative 4 to 5. And the interval from 5 to infinity. So the boundary points divided the real number line into 3 intervals. Now what we want to do is to decide which interval will satisfy the original inequality. All right? So what we want to do here to find out or to make a determination, in each interval, say from a -4, for all real numbers less than a -4, so we're going to choose what we call a test value. So choose something less than a -4. So let's choose, let's say, a -5. So I'm going to write, all right, the test value. All right. So in this interval, I'm going to choose a -5. And now what do we do with that? We now want to substitute. All right. In other words, we want to evaluate x squared minus x minus 20 when x is equal to a -5, and see if f of x is greater than 0 or less than 0. All right? So let's see what we have here. So we have a -5, plug it into, all right? So we have a -5 squared minus a -5 minus 20. All right, if we do this, what do we get here? We get 25 plus 5 minus 20, which is what? Which is 30 minus 20, which is 10. All right, and we find that it's positive. All right, so the conclusion, let's keep track of our conclusions in each case. All right, so the conclusion for this test value, or for the interval for all real numbers less than a -4, we conclude that f of x is greater than 0 for all values of x in the interval from -infinity to a -4. All right. Now we move on to the second interval, the interval from a -4 to 5. So again, we need a test value. Choose a real number between a -4 and 5. So let's choose 0. All right, and we want to determine whether or not f of x is greater than 0 or less than 0. So in this particular case here, we have, so let's substitute again into x squared minus x minus 20. So we got 0 squared minus 0 minus 20, which is going to be 0 minus 20, which is a -20. And this is negative. All right. So our conclusion is that in the interval from a -4 to 5, f of x is less than 0 for all x in the interval from -4 to 5. Now the last interval, the set of all numbers greater than 5. So we want to pick a test value greater than 5. All right, so let's choose 6. All right, and now we evaluate the function at 6. So we have 6 squared minus 6 minus 20. So 6 squared is 36 minus 26, which is what? All right, which is 26 minus 26, 36 minus 26 is 10. All right, and this is what? This is positive. All right, so the conclusion is that f of x is greater than 0 for all x in the interval from 5 to infinity. All right? So now the solution set. So the solution set, all right, we want to write the solution set, selecting the interval or intervals that satisfy the original inequality. All right, so we want it greater than 0. X squared minus x minus 20 is greater than 0. So it's the interval, all right, for all x less than a negative 4, and the interval where x is greater than 5. All right? All right, so the solution set the solution set consists of, so let's write it as minus infinity to a negative 4 union the interval greater than 5. The set of all real numbers greater than 5. All right? So this is the solution set. We can also express this in what we call set builder notation, as you recall. The set of all x such that x is less than minus 4, or x is what? Greater than 5. All right, we want to graph the solution set. So we're going to graph the solution set on the real number line. So if we graph this solution set, I'll put the graph here. I'll put it here. So if we graph, we have a negative 4, 5. All right, so the set of all real numbers less than a negative 4 would be here, and everything to the left of a negative 4. And the set of all numbers, real numbers, greater than 5. So this is going to be, and everything to the right of 5. In the next example, we want to solve a rational inequality. So we're going to solve and graph the solution set for the given inequality. 2x divided by x plus 1 is greater than or equal to 1. All right, so again, the first step here, we want to rewrite that inequality in this form. F of x is greater than or equal to 0. So let's do that. So we have 2x divided by x plus 1 minus 1 is greater than or equal to 0. All right, let's simplify this. So we're going to simplify this, and we get what? 2x minus 1 times x plus 1, all divided by x plus 1 is greater than or equal to 0. Let's simplify. We have 2x minus 1 divided by x plus 1 is greater than or equal to 0. All right, so what do we have? Combining like terms, we have x minus 1 divided by x plus 1 is greater than or equal to 0. All right, so this is the rational inequality that we will deal with. All right, so the first thing, we want to find where this rational inequality is equal to 0. All right, to do that, all right, where it's equal, we're going to solve x minus 1 is equal to 0, so x is equal to 1. So this 1 will serve as a boundary point. Also, when dealing with rational inequalities, we also want to know when it's undefined. It's undefined when the polynomial in the denominator is equal to 0. So when x plus 1 is equal to 0, we find that x is equal to negative 1. All right, so this is where it is undefined. All right, and this is where it is equal to 0. Undefined equal to 0. Now we're going to use these 2 points, 1 and minus 1, as our boundary points. All right, and the boundary points divide the real number line into intervals. So in this particular case, so we have, let me do it over here. So we have minus 1, the number line. So we have what? We have minus 1 and 1. All right. And these boundary points, minus 1 and 1, divide the x-axis, the real number line, into 3 intervals. Namely, let's see, the set of all real numbers less than a negative 1. All right. All of the real numbers between a negative 1, greater than a negative 1, and less than 1. And all real numbers between 1, greater than 1. All right, so the boundary points give us these 3 distinct intervals. Now, just as we did in the other problem, the previous problem, when we were solving the polynomial inequality, we now go and use the same steps that we used there. In other words, we want to, in each interval, we need to test a number. We have to choose a number in each interval and decide if f of x is greater than or equal to 0, or if it's less than or equal to 0. In this particular case, we are interested in f of x being greater than or equal to 0. All right, so we're going to test each. All right, so let's see our intervals again. Let's do the same thing that we did before. So the interval, all right, we have what? Negative infinity, negative 1. We have the interval minus 1 to 1. And then all real numbers greater than 1. So these are the intervals. All right? Now we need a number to test. So in each interval, let's choose a real number that lies in the interval. So a real number less than 1, let's choose a negative 2. So I'm going to just put test number, the number we're using to test. So it's going to be a negative 2. All right, and then let's do the calculation. Let's substitute. All right, so we're substituting into, so what do we have here? All right, so we test, we got x, where x in this case is a negative 2, so we have a negative 2 minus 1 divided by x plus 1. So this is a negative 2 plus 1, so we get a negative 3 divided by a negative 1, which is 3, and of course this is what? This is positive. All right? So the conclusion, all right, the conclusion is that f of x is greater than 0 for all numbers in the interval from a negative infinity, -1 in that interval. All right, in the next interval, the numbers between greater than a -1 and less than 1. So let's choose a test value there. So we're in this interval now. All right, so let's choose 0. All right, so we're choosing 0 to test. So let's evaluate. We have, this is x minus 1 divided by x plus 1. When x is 0, we have 0 minus 1 divided by 0 plus 1, which is what? A -1. All right, so this is now negative. All right. All right, when we evaluate the function at 0, we get a -1. So the conclusion is that f of x is less than 0 for all numbers, all real numbers, x in the interval from a -1 to 1. And now, in the last interval, the set of all numbers greater than 1, let's choose 2. We're in this interval now. So if we choose 2, the test number is 2. So let's evaluate x minus 1 divided by x plus 1. So we have 2. So we have 2 minus 1 divided by x plus 1. X is 2, so this is 2 plus 1. So we get what? 1/3, which is positive. So the conclusion is that in the interval from 1 to infinity, f of x is what? Greater than 0 for all x in the interval from 1 to infinity. All right? Now, because the inequality in this case involves greater than or equal to, we must include the value when the function is what? Equal to 0. All right, so f of x is equal to 0 when x is 1 in this case. All right, this is what we found. All right, when x minus 1 divided by x plus 1 is equal to 0 when x is equal to 1. So therefore, since it's greater than or equal to 0, it's equal to 0 at 1, so we must include 1 in the solution set. Right? So the solution set, all right, is the interval, so greater than 0, here's 1, greater than, all right. So we have the interval, the set of all real numbers less than a -1, union all of the intervals greater than 1. But because the function is equal to 0 at 1, 1 is included in the solution set because the initial condition is that f of x be greater than or equal to 0. So it's equal to 0 at 1. So we have to include 1 in the solution set. So that's union 1, the set of all real numbers greater than 1. All right? And then it says graph the solution set. Let's graph this. If we graph it, all right, we can use this to graph it. It says that, all right, I'll just write it over. All right, here's a -1, 1. So for all real numbers less than a -1, so it's this and everything to the left. And the set of all real numbers greater than or equal to 1, we're including 1, so we have the bracket and everything to the right. So this is the solution set in interval notation as well as a graphical representation of the solution set.